Okay, welcome to this third and final video on molecular structure. This video is going to be a combination of the last two videos, so we're going to be using the Vesper model to draw molecules and the AXE method of counting electrons. So in this video, I'm going to draw the molecule and give you the geometric shape. I'm also going to be giving you the bond angle it forms and the hybridization. So our first example is going to be carbon dioxide. So carbon has 4 valence electrons and oxygen has 6, giving us a total of 16 valence electrons. We're going to subtract the highest multiple of 8, giving us 0, divide that number by 2, still 0. So we're going to have a configuration of AX2. Now the AX2 configuration is a linearly shaped molecule. So we're going to have our central atom, the carbon, has a smaller group number, linearly bonded to the oxygens. Now the carbon is in the first two periods, so it's going to follow the octet. To do that, we're just going to add some double bonds. The surrounding atoms always follow the octet. Okay, so there we go. Now it has a steric number of 2. So a steric number of 2 has a 180-degree bond angle. Since we don't have any electron lone pairs, it stays true to that bond angle. Now the hybridization here is going to be sp hybrid. Okay, the next molecule we're going to look at. So we're going to look at nitrogen dioxide anion. So here we have nitrogen with 5 valence electrons, oxygen with 6, giving us a total of 17 valence electrons. We're going to add one more for the charge there. We have a total of 18. From here we're going to subtract the highest multiple of 8. We're left with 2, divide that by 2. So we're going to have an AX2E1 configuration. Now the AX2E1 configuration gives us a bent molecule. Okay, so we're going to have nitrogen, smaller group number in the middle, bonded by 2 oxygens in a bent shape, and 1 electron lone pair. So nitrogen is in the first 2 periods, so it has to follow the octet. We're just going to add another double bond there to fulfill it. And the surrounding atoms always follow the octet. Now, since it is an anion, we have to draw the brackets and the negative charge. Now, this is the resonance structure. I'm just drawing one of them here. You could also have drawn the double bond on this side. So, AX2E has a steric number of 3. The steric number of 3 has a 120-degree bond angle. Here, since we have an electron lone pair, it's going to be a little less than 120 degrees. So the bond angle here, a little less than 120. We're going to have an sp2 hybridization for this molecule. Alright, let's do a few more. So we have for our next molecule is iodine pentafluoride. The iodine and the fluorine both have 7 valence electrons. We're going to have a total of 42 valence electrons. We're going to subtract the highest multiple of 8. Divide that by 2. So we're going to have an AX5E1 configuration. Now the AX5E1 configuration gives us a square pyramidal geometric shape. Okay, so we're going to have our central atom, the iodine, because it's less electronegative, surrounded by 5 fluorines. And 1 electron lone pair. Okay, so it has a steric number of 6. The steric number of 6 has a bond angle of 90 degrees. However, since we do have a lone pair, it's going to be a little less than 90 degrees. So the bond angle between these guys, all of them, is going to be less than 90 degrees. For this molecule, the actual bond angle is 81.9 degrees. Depending on what you have bonded, it's going to change. So, again, just less than 90 degrees is what you need to know. Okay, let's just do a couple more. A few more examples here. We have another anion. We have phosphorus with 5 valence electrons, fluorine with 7, giving us a total of 33 valence electrons. So from here we have a charge here. We have an extra electron we need to account for. So we're just going to add one more, giving us 34. So from that, we're going to subtract the highest multiple of 8. 8 times 4, and then divide that by 2. Giving us 1. So we're going to have an AX4E configuration. Now the AX4E configuration gives us a seesaw shape. So we're going to have the phosphorus in the middle, surrounded by 4 atoms, the fluorine, and 1 electron lone pair. So again, the phosphorus is in the first 2 periods, so it can break the octet. The fluorine surrounding atoms always follow the octet rule. Since it does have a charge, remember we got to put it in brackets and indicate that. So the AX4E1 configuration has a bond angle of, steric number of 5. Steric number of 5 has a bond angle of 90 and 120 degrees. So here we're going to have a bond angle of a little less than 90 and a little less than 120. So from here to here, it's going to be less than 90. And then among these guys here, we're going to have a little less than 120. So the hybridization for this is going to be 5. So we're going to have sp3 dehybridization. sp3 dehybridization. Okay, let's just do one more. We'll do one more to wrap up the video. So we're going to have bromine tetrafluoride. So the bromine is in the 7, has 7 valence electrons. The fluorine also has 7. Total of 28 valence electrons. We're going to subtract the highest multiple of 8. 8 times 3. And divide that by 2. Gives 2. So we're going to have an AX3 E2 configuration. Now the AX3 E2 configuration gives us a T-shaped molecule. So we're going to have the bromine in the middle because it's less electronegative. Surrounded by three fluorines. And 2 electron lone pairs. Okay, so we're just going to fill out the octet for the surrounding atoms. And the bromine doesn't need an octet because it doesn't fall in the first 2 periods. So here's our molecule here. It has a steric number of 5. Again, steric number of 5 has 120 and 90 degrees bond angle. So from here to here, again, since it has electron lone pair, it's going to be less than that. So from here to here, it's going to be less than 90 degrees. Now the 120 degrees would be between this atom here, and if we had atoms here, it would be between these. But since it has electron lone pairs, it doesn't form an angle, so it's going to be less than 90 degrees. The actual bond angle that this molecule here forms is 86.2 degrees. again, it's less than 90. The exact number is not important, just know that it's less than 90. And that's going to do it for this video.